Hello everybody, in this lecture we will be solving 1988 IMO problem number 3. Here is a view of this problem. A function f is well defined with the following. For even numbers it is defined as such, and in the odd case, depending on if it's equal to 1 mod 4 or 3 mod 4, the domain element, the function maps it to the corresponding terms. Okay, so this function works for all positive integers n. Determine the number of positive integers n less than or equal to 1988 for which f of n is equal to n. So basically we need to find the fixed points of this function. Well, the fixed points less than 1988 of this function. What I did is I went ahead and produced some results here. It took me probably about 1 or 2 minutes to came up with this. So let me bring them next to the definition, the formula, and then we can discuss the implication. So we have the closed form here, and then the evaluated values here. Okay, so staring at these numbers over an extended period of time, eventually you can come up with the following observation, that the key is the binary. Basically the key is to look at the binary. So let's rewrite all these numbers in binary form, in base 2. So therefore this one remains, this one remains, this one would be equal to 11, this one is still 1. Well, yeah, let's just come up with a new column here, I guess. So this is 1 0 1, that one would be 1 1. 7 can be represented as I think 1 1 1, right? 1 plus 2 plus 4, and then we have 1, and then we have 1 0 0 1, 1 plus 2 4, yeah, and then this one would be 1 0 1, so 1 plus 4. This one would be 1, and then so 13 would be 8 plus 4 plus 1. And this one would be again 1 1. That one is 11 would be, I think I did it no, I didn't do it earlier. So it is 8 plus 2 plus 1, and 7 would be just 4 plus 2 plus 1. This one is 8 plus 4 plus 2 plus 1 again. 1 0 0 0 1, 16 plus no 8, no 4, no 2, and then this one is again 1 0 0 1, and 25 would be 16 plus 8 plus no 4 in it, no 2 in it, and then 1. Finally 5 is, we did it earlier, 1 0 1. So when you look at the binary representation, life is okay, but the idea is the following. If you look at the numbers that are mapped to which the n's, so in mod 10 they are 1, not mod 10, I should say base 10. So we have our numbers, and somehow they are mapped to f of n in base 2. So this is the new column that we just produced. 8 9 10. Okay, so this in mod so in base 1, so this one is 1 0. Okay, this one would be 1 1, that one is 1 0 0, and that one is 1 0 1. 6 is 4 plus 2, and then this one is 4 plus 2 plus 1, 8 plus no 4, no 2, no 0, no 1, I should say, 8 1, and then this one is 8 no 4 1 0, right? and so on, right? So do you see any correspondence between these numbers and these numbers? Please check them and think for a minute what they represent. By now you probably guessed what's going on. So I assume you guys paused here and then trying to figure out the relationship. But the idea is simple, right? So F, the mapping F, simply reverses the binary representation of n. So here n is 1, reversing the representation, it's 1 again because it is symmetric. But 10 becomes 0, 1. So there's an invisible 0 here. And 11 becomes 11, that's clear. 100 becomes 0, 0, 1. 101 is the same as 101 because it's symmetrical. 110 is equal to 011. 111 is the same as 111. 1000 is 0001. 1001 is 1001, so clear. This one becomes 0101 and so on. So this is obvious, so let's write that down. So here we claim F reverses the binary representation of n, basically. So F reverses this representation. Okay, proof. Consider G defined by the following. If n is equal to Cm, C sub m minus 1, C sub m minus 2 in binary representation, C2, C1, C0 in base 2, and Cm is here 1 because the leading coefficient has to be 1. Then, so if that, then actually I don't okay, let's just leave it like this. Then G of n is equal to C0, C1, C2, Cm minus 2, C sub m minus 1, C sub m in base 2, and obviously the possibility for leading zeros are on the table as well. But that's it. So now what I claim now, in order to finish the proof, so in order to finish the proof of this claim, all we need to do is to show that f of n is equal to g of n for all n. And that's it. So if we can prove that, then it is clear from this description that G does in fact do this reversing business of the binary representation. So F would have done the same trick as well. Now one can easily show that G of 1 is the same is equal to 1, and G of 3, because the representation of 3 in binary representation is 1 1. So you reverse it, it's again 1 1. So this is equal to 3. So G of 1 and F of 1 agrees, and G of 3 and F of 3 also agrees with each other. So for the rest, all we need to verify is that the function G obeys the same recursion relations as F does, and that would immediately prove the desired claim. So for this, consider an arbitrary positive integer n, which can be written as Cm, like we did earlier, Cm minus 1, C sub 1, C sub 0 in binary, with leading coefficient C of m is equal to 1. Then let's observe what's going on. So then 2n is simply equal, it will just shift all these digits to the left, Cm minus 1, C1, C0, and it will simply add a 0 at the end. Then 2n plus 1, 2n plus 1 is similar, except that at the very end you will have the digit 1 instead of 0. C1, C0, 1 in binary. And 4n plus 1 is simply, remember, I need all these so that I can establish each of these results. 1, 2, 3 results. Okay, so 4n plus 1 is simply equal to, well, when I divide by 4, I'm moving 2, shifting two digits to the left, but then I need to add plus 1, so therefore it would become Cm minus 1, C1, C0, 0, 0, but then adding a 1, so it's a 0, 1. And finally 4n plus 3, the same thing, Cm, C sub m minus 1, C sub 1, C sub 0, and then 0, 0, but adding 3 is adding 1, 1, so which is just 1, 1 in binary. Okay, so according to the definition of G now, we can conclude pretty quickly. So G of 2n, so you have this binary number here, so you just reverse the digits. So the 0 will be in the front, it is useless, so it would become C0, C1, all the way to Cm minus 1 Cm in binary. And this, by the definition of G of n, recall G of n reverses the order, so that would be the same as G of n. Next would be G of 2n plus 1. G of 2n plus 1. Recall 2n plus 1 is equal to this expression, so when I reverse it, I will get 1, C0, C1, Cm minus 1, C sub m in binary, and that's simply equal to, I can just take out the 1, or I can basically split this sum into as follows: 1, 0, 0. So you have a bunch of zeros. In fact, you have m plus 1 zeros plus C sub 0, C sub 1, C sub m minus 1, C sub n base 2. But notice that this is simply equal to, so for this one, the first term is simply equal to 2 to the power m plus 1. So this is 2 to the power m plus 1 plus, and the second term here is simply equal to G of n, right? So it's the same, G of n. Now we continue in the following manner. So 4n plus 1 is equal to, remember 4n plus 1 is equal to this expression here. When you reverse the order, so we will have a 1 followed by a 0, and then C0, C sub 1, all the way to C sub m minus 1, C sub m in binary. But again, splitting it, in binary, here you would have m plus 2, m plus 1, m plus 2. I think there is m plus 2 zeros here. M plus 2 plus, and then you have the remaining term, which is C0, C1, all the way to Cm minus 1, Cm in binary. So therefore this can be simply represented as 2 to the power m plus 2 plus, and this remaining term is simply G of n again. Finally, G of 4n plus 3 is equal to 4n plus 3 was this expression here. We just reverse it, C0, C1, C sub m minus 1, C sub m in binary, and this is simply equal to 1, 1, zeros, a bunch of zeros. How many of them? Again, m plus 1 of them in binary, plus, and then we have G of n at the end again. So therefore G of 4n plus 3 is simply equal to, so the first one here would be 2 to the m plus 2 plus, the second one here would be 2 to the m plus 1 plus, and then the remaining term here, which is g of n. In fact, we can continue further to liken it to, so making use of this expression and substituting, we realize g of 4n plus 1 is simply equal to 2 times g of 2n plus 1. So if you multiply this by 2, you will get this expression for sure, and you will get 2g of n. So we need to subtract 1g of n because we are over counting. And also similarly for this one, this is simply equal to 3 times this expression. So 3 times g of 2n plus 1. So when we multiply it by 3, so when you multiply it by 2, you will get 2 to the n plus 2, 2g of n, and then a final one will be for 2 to the n plus 1, and then another g of n. So we need to subtract 2g of n. 2g of n. But now, when you compare it with the identities, so comparing these expressions, so this is the expression for g of 4n plus 1, and this one is the expression for 4n plus 3. Going back to the original condition, obviously we also have this one, g of 2n is equal to g of n, and this one is g of 2n plus 1. I hope it is clear that the function g and the function f, they coincide. So this is exactly the same representation for each one of them. We early on got g of n is equal to f of n, g of 3 is equal to f of 3, so those are satisfied. G of 2n is equal to g of n. So we got it here. And finally, these last two results here are the same as those two here, this one and this one. Okay, so now we are done with the first part of the problem. Now in the second part, all that matters now is to figure out the fixed point of this function f, or so therefore so we established therefore f is in fact identical to g. Now we need to figure out the fixed points of f such that f of x is equal to x for x less than or equal to 1988, sorry. 1988. Recall x is a positive integer. Okay, so what this means is that for a positive integer n, with a binary representation cm minus 1 all the way to c sub 1, c sub 0 in binary with leading coefficients and leading digit 1, it satisfies f of n equals to n if actually if and only if, so it's an if and only if statement. If and only if so if the binary expansion is symmetric. If and only if c sub 0, we reverse it, and we are expecting, so this is the value f of, so this is f of n, and in binary, and c sub m minus 1, c sub 1, c sub 0, and this is n in binary. So for these two to coincide, it must be the case that the binary expansion of n should be symmetric, going left to right and right to left. So what that means is that so this implies c sub k is equal to c sub m minus k for k equals from 0 all the way to m, and we usually call such numbers as palindromes, as you remember. So this question reduces to counting the number of palindromes in binary, such that so the less than 1988. So in binary 1988 is simply equal to 5 ones, 1 2 3 4 5, 1 2 3 zeros, 1 and 0 0. So it consists of so this is the binary representation of 1988. All we need now is to count the palindromes that are less than this number, basically. So this shouldn't be too hard, actually. If you focus on you can go interval by interval, right? So for instance, if you consider the interval 2 to the 0, 2 to the 1, which is simply equal to 1, 2, the integers in that interval, which happens to be only 1, and obviously this is a palindromic number. And then if you go on to the following interval, so this is closed, this is open, so 2, 4, we have the numbers 2 and 3 in this range, and in binary they would be represented simply as 1 0 and 1 1, and of these only one of them. So let's count the number of palindromes. We had one palindrome here. Here we have again one palindrome, and in this range, 2 squared to 2 cubed, namely between 4 and 8, 4, 5, 6, 7 are the integers. When you write them in binary, you will get 1 0 0, 1 0 1, 1 1 0, and 1 1 1. Of these, you can easily establish that this one and that one are binary. So we have two palindromes, 2 are palindromes, and so on, right? So you can continue in this fashion: 2 to the 4, 8 to 16, namely all the integers from 8, 9, all the way to 15. Their binary representation would be 1 0 0 0, 1 0 0 1. Let me show one more time, right? So 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, and 1 1 1 1. I hope that's reasonable. So we have 8 such numbers. Of these numbers, we have 1, 2. Again, 2 palindromes. So this this makes sense in the following way. So anytime you have, for instance, we don't have to write all these numbers. So all the integers in this range, 2 to the m, in this interval, will have m plus 1 digits, binary digits, right? So m plus 1 binary digits, and depending on whether m is odd or even, we can easily count. So for instance, if m is even, in the first case, if m is even, then there will be our number will become like c sub m, c sub m minus 1, all the way to c sub because m is even, m over 2, c sub m over 2 minus 1, all the way to c sub 1, c sub 0 in binary. Now to make this a palindrome, so cm must be equal to c0, but recall that cm was equal to 1, so there is no choice for that one. So cm is equal to c0 equal to 1. But then for the remaining terms, so all these terms are matched to these terms here, and in fact we have I believe we have let me hold it. So let's there must be no, this guy is in the middle. Sorry for that. So there's a middle term because we have an even sequence, right? So there's an m over 2 plus 1 term here. Okay, so these terms have to be the same as this. So what I mean is c sub m minus 1 is the same as c sub 1, and so on. So therefore we have in total m over 2 minus 1 choices here, and then one more choice here. So in total we have m over 2 choices, which tells us that there is in total there will be so when I say choices, a choice between 0 and 1, because we are considering binary, there are this many palindromes when m is even. In a similar way, when m is odd, then it's not difficult again to realize that there will exist 2 to the m minus 1 over 2 palindromes. So therefore, because we have 11 digits, the palindromes smaller than, so obviously 1988 is less than 2048, which is 2 to the 11, which is simply a 12-digit binary number. So there are 11 zeros here. So therefore, we're only interested in 11 digit binary numbers, and we want to figure how many palindromes exist among those. So all we do therefore is we can start the count. We already started here actually, 1 1 2 2. Well, this perfectly fits the description of our formula here, obviously. For instance, if m is equal to, start with 0 here, you will be the first choice here. So it is m is 0 would be 2 to the 0, which is just 1, so it works. And then when m is 1, we are in the odd case, so substituting 1 here, 1 minus 1 is 0, 0 over 2 is 0, 2 to the 0 is again 1, so that works. So this formula looks reasonable. So therefore, the number of palindromes, how do you even spell palindromes? Okay, so palindromes in total would be equal to yeah, so it would be let me just use the formula, right? So in summation sign, m over 2 when m is even, right? So m even, well, when I say even, I mean 0 2 4 6 8 and 10, plus the summation of odd. When m is odd, we have m minus 1 over 2 palindromes, and when I say odd, I mean 1 3 5 7 and 9. And therefore this count, when you do it, for instance, we get 1 plus 2, so this is our first count. Yeah, when we plug in 2, for instance, we get 2. When we plug in 4, 2, so we get a 4, all the way to when we plug in 10, 2 to the 5th power, which is 32, plus, and the same thing on the right one, except that here we will have only 5 terms, 1 plus 2 plus 4 plus 8 plus 16. We will stop at 16. So the sum here on the left is 63, plus the sum here would be 31, which is 94. However, we overcounted here because we counted all the palindromes less than 2 to the 11. There are 2 more palindromes between 1988 and 2048, namely where do I have 1988 here? Oh yeah, okay, so namely the palindromes which is in this range are those which are 1 1 1 1 1 0 1 1 1 1 1 or 1 1 1 1 1, and then in the middle I put a 1 1 1 1 1 1. So these are the 2 palindromes which are greater than 1988 but still strictly less than 2048. So therefore I need to subtract 2 to come to the final count of 92. So therefore our conclusion is that there exist 92 fixed points which satisfy f of n is equal to n for n less than 1988, and that solves the problem. Hope you enjoyed it, and looking forward to see you guys in our next video.